are fit and well, enjoyed the evening yesterday, had a look at the stars and had a look at the sky, as it was relatively clear, and I think there was certainly some good pictures of the moon. So it was quite a pleasant evening yesterday. Very happy to have seen that myself. Couple of things I just want to mention for you today. I'm going to go through the final part of the presentation. I'm going to also give you your project that you're going to work on for the astrophysics, and this will allow us to give you some time. It's going to be a group project, so you're going to be working in groups of 3 people. It's going to be to put together a presentation, and you will make that presentation to me as a teacher. So one of the lessons that we will do after Easter time will give you the chance then to make that presentation. I'll tell you where you'll find more details after we finish the presentation work today. Just one point of order. A number of people appear to have logged on today using non-school addresses, which has meant that I need to give you permission to enter the classroom. As a general rule, we don't want non-school email addresses logging into the system. So please, can you make sure next time you enter, okay, you did need permission even though you used your email. I don't know why it is that some people appeared to have needed it, some didn't, but okay. Well, just in case, please, I checked the setting in my Meet, and I do, let me just have a look again. There is a security setting which says quick access. When turned off, everyone who isn't invited must ask to join. So I've turned that on, which means ideally, if you've been invited, you shouldn't need to log or request. But okay, if it's a glitch in the system, I'll talk to the IT people, but not a problem. And thank you for letting me know that. It's important that I am aware. Now, I've had chundering in the background, my printer printing out my materials so that we can go through. Because it's a link, we aren't actually invited. Well, yeah, I understand that, but most people came in without having to request. Let's not worry about it. If you're logging in with the school email, not a problem. I will just have to keep on admitting, and I will send a request to the school to find out if there's a reason why this is happening. Right, I had 1 or 2 emails yesterday and some comments back from yesterday's presentations. I understand from you that they were a little long. On the other side, quite a number of you said you found them very, very interesting. So I'm pleased about that. Now, I am in the process, for those of you that are interested, preparing some additional materials. Now, I said about the medical material, that is now printed and ready. So I know that there's at least one person that wants the medical material, but we're going to have some similar material for the astrophysics, which will go considerably deeper than we're going to cover in the class lessons. But it will give you some more work. It will give you some more suggestions, and it will give you a lot more information. But we won't start talking about, what did you say yesterday, strange galaxies or strange matter. That doesn't come into our astrophysics. So that, I'm afraid, you'll have to leave until you get to places beyond IEGS. So, any questions for starting before we make a start for today? Okay, let's just see. Now, I have the presentation running on my other PC, so hopefully you can see that now. Let's just go back. This is the next section that we were due to cover, which is looking at the life cycle of a large star. And just before we do that, let me go back to the previous slide, which was the final life cycle of the small star. And there came a little bit of confusion here towards the end, that what will happen in this death throe of the small star system. And we are talking now of stars that are going to be equivalent in size and possibly a little larger than our sun. And those stars will burn all their energy. Now, I think, as I probably explained to you during the lesson yesterday, or when you asked questions, what will happen during a life cycle is that this will take an inordinate amount of time. And the universe has not been around for long enough for a lot of these galaxies and for a lot of these stars to have gone through their end of life sequence. So what we're looking at here is the end of the life cycle 10, 11, 12 billion years after this star system was formed. Now, the outer layers will be shed off into space. They will just, gravity stops acting. The distances are so large that all of a sudden gravity stops acting on these neutral particles. So the planetary nebula just starts moving further and further apart and sort of drifts off into space. And it's a bit like when you put your cream into your coffee. When you put the cream in, it stays in a blob in the center. But if you rotate your cup or a spoon in your cup, the particles of that of the cream all start to move outwards. Of course, if you stir your coffee long enough, it'll mix into the coffee. But I'm not interested in that. I'm more interested in what will happen when these things carry on outwards. And that's where we set up this thing called the planetary nebula. And the planetary nebula leaves the core behind. So what you can see on here, and I'm on the wrong mouse, it's this one. What you can see on here is what is left behind by the star when it's come to an end. There is no burning, there are no nuclear processes continuing in this star. This star has now achieved its end result. It's like a fire that's been burning, and all of a sudden, all you're left with is the ash. So if any of you have ever looked at a campfire when a log burns, sometimes that log stays in a log shape, even though it's burnt, until you touch it with a stick or something, and then all of a sudden it crumbles up. Well, the same thing is going to happen inside here. But this object is now going to be a hydrogen helium mass. So it's not a solid planet. Now it's going to be at temperatures that could be around 5,000 or 6,000 Kelvin. So it's definitely not going to be a solid mass. This object will then, from the day the planetary nebula has formed, will start to cool down. So over the course of billions of years, this object will go from a shining object in the sky, a white dwarf, gradually getting cooler and cooler and cooler until it gets to the point of becoming a black dwarf. And a black dwarf is simply an object that is emitting no radiation. It is not able to give off any type of radiation once that final death throw has been found. Now, I need just to step back. Did I mention yesterday, just tell me yes, no, please, the brown dwarf? I think we mentioned it, but I'm not sure I told you when a brown dwarf forms.
I don't
Did
think
we mention that?
I think you maybe mentioned it, but didn't go into detail.
Yes, no?
Yeah, you mentioned it, but no details.
Oh, sorry, my volume must be turned down. Try again.
Sorry, you mentioned it,
but I didn't explain. That's what I thought.
Exactly.
Okay, so let me just go back to the first slide on here. So we get to this point just here. Now, I talked to you about this phase where these protons, these are just little positive charges floating around as dust in space. They come together, and if there are enough of them, they will eventually heat up, start rotating around each other, start to feel gravitational influences. But if there aren't enough of those particles, such that you never actually achieve what's called the critical density, the protostar will just fizzle out. It's, again, let's go to the analogy of the campfire. It's like you've got all of your wood stacked up in the campfire, and you've got something you start to light at the bottom, and it starts burning, but then fizzles out. So what have you got left? All you've got left are the pieces of wood that you started off with. So in this example, you've got the protons still left. So you've got inside here, all of these, oops, let's get this again. You've got all of these protons inside here. All of those will stay together, but no nuclear process will take place. And then you will find that you are left with a brown dwarf. Why is it brown? Well, it's slightly hotter than a black dwarf, but it will continue. There will be motion inside there. As you know, rub your hands together, you create heat, you create warmth. So as long as those protons keep moving and keep themselves together in this clump, they will continue to generate some form of heat. So they're not going to just cool down, but they're going to continue rotating and moving. but they will never go critical because they'll never achieve the density that is necessary. And what's left behind in this instance is then what we call the brown dwarf. So we've got white dwarfs, we've got brown dwarfs, and we've got black dwarfs. Wow, what a combination. So let's move on now. Let's get in. Are there any more questions just before I do that regarding the life cycle of the small stars? Just before I move in. Could you could you walk on a black dwarf? No, because the black dwarf, well, having said that, I'm not a chemist, but what will happen to hydrogen and helium as we cool it down and down and down and down to temperatures that are almost absolute zero? If you remember from last year, you would have talked about motion of molecules. That's what causes temperature. The movement of the molecules creating kinetic energy. They're moving around, they're hitting the side of a container, so they're creating pressure. As you get cooler and cooler and cooler, the temperature goes down, and we know, for example, that the intergalactic medium is at around 2.9 Kelvin, just above absolute zero. What will happen to hydrogen and helium at those temperatures? They probably would become solid. So in that sense, yes, you could probably walk on a black dwarf. But let's go from 5,000 Kelvin down to Earth temperature. So what temperature do we have? Around 300 Kelvin. So room temperature for us here in my office is around 300 Kelvin. So if we cooled this this planetary nebula down to 300 Kelvin, what would the hydrogen and helium be? What state would the hydrogen and helium be in?
If it were at 300?
Yes.
Gaseous.
It's still a gas, exactly. Yes. Right. So until you've cooled this black dwarf down to a temperature where the helium and the hydrogen would solidify, then your planet will be your nebula would be a gas-based group. So the white dwarf in this sense is gas-based, right down until the gases sublime and turn into solids. So we're sort of looking at very theoretical ideas here, but only at that point. But I don't know what materials you'd be able to walk on a black dwarf with at those types of temperatures. So yeah, let's think about it another time. Answer your question, Charlie. Okay, I presume so. So let's continue now. The next step of this is to look at the life cycle now of a planet, of a star that is a similar size to the small star, but it goes through a similar life cycle in much, much faster time periods. The end is much more catastrophic, and it leads us to see the generation of some more interesting elements. So, starting off again, just as we did with the smaller star, we start off with a large cloud of gas. And this large cloud of gas, and we're talking now gas clouds which are going to contain 10 times the amount of hydrogen or helium or protons as our sun contained when it was formed. So we're looking now at much, much, much larger gas clouds. We can see evidence of these. Again, this color that you're seeing in here, this color represents the formation area. Now, some of you may have heard of the pillars of creation. These are this wonderful picture taken of gas clouds in the process of forming stars. They are at these sort of levels. They are the amount of protons, hydrogen atoms coming together to start to create, hence the name, the pillars of creation. Now, this continues in the same way as for a small star. However, some differences do start to occur. I need to put that one back. Yeah. And when the protostar starts burning, the first thing you'll notice here is that the color is different. In our previous model, this model burnt in a white sort of yellow color. Now what we've got, with much, much more mass, we've got bigger bodies, we've got more acceleration, we've got denser material. So nuclear fusion begins again, but this star starts to shine and stabilizes again in the main sequence. But what you can see is that it is a different color. Now, logic is going to tell us, even though it's on the main sequence and it's the sort of star that you could see, it is actually a bigger star. Good point here is this type of star, when it is formed, might only remain like this for 10 million years. Think about the difference now. The smaller star burns like it did because it's burning at a cooler temperature for 10 billion years. A much, much more massive star burns much, much hotter, which means that it's going to burn much, much faster, which means that it will probably only burn for around 10 million years, as opposed to 10 billion for the smaller stars. Now, the processes that we talked about last time happen in the same way. When the core runs out of hydrogen, nuclear fusion stops. So the hydrogen burning has taken place. This then stops all of the hydrogen from continuing to burn with nuclear fusion. And what will happen now is you will set up a surrounding shell of hydrogen, and the hydrogen will start to burn and fuse into the helium as it did with the smaller stars. But when the core heats up further, the helium burning and the star begins to form in the same way as previously seen with the small stars. So what we've now got, the core has heated up. Hydrogen fusion is taking place to produce helium. Helium starts burning. The core starts to expand again into a supergiant. So not only have we got now a red star, but we've got a supergiant red star, which is similar in nature, but much, 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 much larger than our previous models. So again, burning continues, the core collapses again, and this time it heats until the heavier metals in the core start to burn as well. And the shell and this core continue to burn to produce now heavier and heavier atoms inside the nucleus. So what's happening here is hydrogen to helium, helium to oxygen, oxygen to carbon, and so on. They will continue to fuse together to create this very hard metal core, as opposed to the previous one where the death occurred with gases in the core. So we've now got heavier elements starting to be formed in the core of this supermassive red giant. And this process, again, continues until the star is ready to collapse. So what we've got, just get my pen again, what we've got is the central hot, super hot region, hydrogen, helium, heavier elements, right out to here, where we've got now iron, we've got all sorts of solid materials that are going to be produced inside this core. But that's not the end. What's now going to happen is the final collapse of this star. And this will happen very, very quickly. And this creates a massive explosion, the explosion called a supernova. And what happens with the supernova, and we can, whoops, why won't this go back? There you go. And you can see now what has been formed. So we've gone from this super, super massive star to what looks to be a tiny remnant. And the tiny remnant that is left in this instance is what we call a neutron star, or if the gas cloud that created this original explosion was large enough, we get the formation of a black hole. So we've gone through the same processes and we've gone through the same death throes, but the difference this time is that there is now virtually nothing left, which is actually quite important for us because neutron stars contain super, super, super dense matter to the extent that if I had a teaspoonful of neutron star matter, that would be the equivalent of several thousand tons of material. I don't think it's quite the weight of the Earth, but it's a very, very dense, very, very nasty, high gravitational environment. As I said to you, when the neutron star is formed, this will happen with a certain size of star. If that star is big enough, And we're talking now stars about 10 times the size of our sun that will collapse to create a black hole. And we are going to look at that in another lesson. I don't think I'll get onto that today. So we've gone through now the life and times of what's happening in all our environments to show us how life changes, how the cycle changes for different types of stars. What I think we can start to see is that these processes lead us in a very, very difficult and different direction. And the life cycle tells us that as we're looking at our objects, we see how these objects are produced. I'm going to go through, the next slide is going to show you a little bit more about neutron stars. And I did want, I think, to just show you something else before I move on to give you some of the activity that you're going to do. So any questions on large star life cycles? As I said to you, when you do your test, your class test, at the end, right at the very, very, very end, this will be one of your questions, the life cycle of a small or a large star. How fast is the supernova event? Great question. It happens instantaneously. It is an event that is over within 3 or 4 days. We have observed supernova, and there are many projects, telescope projects, that are active at the moment looking for supernova events. So they are looking for example, red supergiant stars that appear to be unstable. Now, have we ever observed a supernova as it happens? Yes, we have, but accidentally. What tends to happen is that astronomers will see an event. So all of a sudden, a particular place in the sky lights up. A supernova took place. So all telescopes are trained on that area very, very quickly. But the supernova has already taken place. What's now happening are a number of telescopes, and the largest telescope, Earth-based, that is being built now in Chile, is going to do sky surveys every few days. So it will scan the sky. This is a 20-meter telescope, which has a 20-meter mirror in its base. This is going to scan the whole of the sky every 3 or 4 days so that it can see an event when something, if something changes. So technology is with us, supercomputers can compare images from 3 days ago to today. So if you can see there's been a change in a particular star, and there are certain criteria that are highlighted, then maybe you can forecast when this event may occur. But when it occurs, it goes very, very quickly. You will see, for example, supernova have been recorded. The classic is the 1066 Crab supernova, which resulted in the formation of a black hole, Cygnus X1. That happened in 1066 and was recorded in Norman documents, or the Bayeux tapestry, that lit up the night sky for 5 or 6 days after the event occurred, and then petered out to what we see a remnant, which is an expanding cloud of gas, or gas and heavy metals. Any other questions? Right, so continuing. I've said to you that a certain process takes place after a certain size of star goes through a supernova, and the sizes are critical. As you can see here, we say anything after a 1.4 to 2 solar mass star has exploded, only the inner core of the star remains. All of the outside, the heavy metals, the gases, everything else has been sent out into intergalactic space. Those materials, so heavy metals, are produced during a supernova. Temperatures are colossal. They are millions of degrees. So fusion is taking place of much heavier elements. So uranium, heavy atoms are formed and become part of the cosmic dust. So that then becomes the type of dust that mixes in with the clouds, with the hydrogen, to start creating heavier types of stars. Oop, which one is it? So what has happened now, the core has a radius of around 10 kilometers. So it's the size, less than the size of a city. The density is going to be 14 orders of magnitude higher than that of the sun. So we've now taken an object that's 1.5 times the size of the sun and contracted it into an object that is only 10 kilometers in radius. And that means that we've now put these particles so close together that they have the density of an atomic nucleus. And this is a neutron star. Now, what you'll find is, and this is the really, what shall I call it, confusing part, the outer shell is thought to be composed of a solid crust of atomic nuclei. But inside, it's a liquid interior composed almost entirely of neutrons. Why neutrons? Any guesses? Why neutrons in this central core? Clue is neut. What are neutrons? Stable, definitely. Neutral, yes. Neutrons have no charge, so there is going to be no electrostatic interaction. There will only be gravitational pull between those neutrons. And at the center, you can see the density achieves around 10 to the power 18 kilograms per cubic meter, which means this is a pretty hostile place. Standing on the surface, this crust of a surface of solid material, where you're being pulled by gravitational masses that are so large, you would simply be crushed to death. You'd be crushed much, much, much before you got anywhere near to the surface. So all of that helps us in understanding the nature of these stars, but their nature is, of course, only a part of the story. Now, I've said to you now that the neutron star is one of the death throes. I'm not going to cover black holes in the same lesson. I will go through that. It deserves a lesson on its own. So we will go through that at a separate point. But I do want to continue to go now to see where we can put these objects. Now, I talked to you yesterday, mentioned briefly the Hertzsprung-Russell diagram. If we look at temperature and luminosity in this diagram, it allows us to see how these stars are formed. So we place luminosity here of an object comparable to the sun. So the sun sits at this level just here. Oops, you can't see that, can you? The sun sits at this level just here because its luminosity compared to the sun is going to be 1. So the sun will fit somewhere across this line just here. And as we look at different stars, now we know the temperature of the sun is going to be around 6,000, so it's going to be sort of in this region just here. What we can also do is put all of the types of stars that we've looked at into different places on this chart. So I can now move on and show we can put, I'm just going to put these stars into their positions. So we've got a relatively cool star down here. So its temperature, 1700 Kelvin. Its luminosity, less bright than the sun, but can I move that? Yes. Just move that down. Its luminosity, 6, which is going to be about 6 times less than the brightness of the sun. We can then put other stars. So we've got another star, hotter star, and continue with all of these. Now, what you can see here, we talked about bigger stars having much brighter luminosity. So you can see the temperature, these blue colored, much bigger stars up here, higher temperatures, as opposed to these stars down here, which are much smaller, much less intense, and much cooler. And so I can continue to put other stars in their positions. Now, we talked about the death throes. So what happens? Oh dear, my computer's logged out. Why has it done that? Let me pull the other presentation. Where's my mouse? There. Sorry about that. I meant to try and change the timer on my other PC, but it didn't work. So can you see? I can't see the other PC now. Can you see the presentation? Can you just tell me?
We can.
Yes.
Yes,
Okay.
we see.
Good. So let's just go through again. So we get through to the 1, 2, 3, 4. So yes, now if we get to the red giants, what we've got to do on this diagram is put this star, remember we've seen this star with a telescope, so we've decided that it has a luminosity that's going to be about 100 times greater than that of the sun. Its temperature is much, much cooler. So if we put that on the chart here, we see that it's going to be at a cooler temperature, but much, much brighter. So it fits well above the main sequence stars. Now you'll see there are a couple of examples here. Regal is also a supergiant. It's not a red giant, but a supergiant star. High temperature, very, very, very bright, which is burning well above the main I keep forgetting you can't see this, can you? So here you can see the main sequence. These stars just here sit well above the main sequence. And we can continue with this if we look at other stars. Let me put that back again. Where we can see now this star, which is a very, very hot star, but very low intensity. So let's put that on the chart just here. And what we find is there is a region down here where all the white dwarf stars sit on this curve. Well, question comes in here. All the white dwarfs lie below this region. All the red giants lie above this region, and all of the normal stars sit on the main sequence, this area in the center. So why do you think that black holes are not included in this diagram? You're absolutely right. There is no intensity, so we can't see a black hole. It has no light luminosity, so we can't put an object with zero luminosity onto the chart. It just is a meaningless position. Oh, come on. Right. Right. Now, having completed the Hertzsprung-Russell diagram, what that now allows us to do is to see the complete universe on a single chart. And you can look online onto various different websites, and you'll find different versions of this Hertzsprung-Russell diagram. And the interesting thing is there are now thousands upon thousands of stars that have been measured, their luminosity relative to that of the sun, their color and temperature based upon what we are observing, and they fit into these regions. So now when we draw the Hertzsprung-Russell diagram, and you'll need to look in your booklet to find this, and there is a fairly comprehensive diagram showing the Hertzsprung-Russell diagram. I'm just trying to see if I can find it, which of course I can't at the moment. Whoops. Trouble is I printed my notes out and they're not bound together, so I don't actually have them all listed nicely like your booklets. So I'll have to come back to that. So having covered now life cycles, Hertzsprung-Russell, that tells us how we can put these stars into their life environment, it gives us now the opportunity for you to do your project. So what is your project? Well, if you have, and I hope that you have your booklet, you should be able to turn to page 3 in your booklet. And at the bottom of the page there, it should say Structure of the Universe Research Project. Any of you got your booklets?
Which booklet are you talking about?
The one that you've just got for the Modeling the Universe. That's, in case you hadn't realized, that is what we're talking about. Yours skips page 3. Is there not a section at the bottom of your section where it says all of the typals, main sequence, red giant, neutron star, black hole, supernova, binary, quasar, radiation? And at the bottom of that page, there should be a thing that says Structure of the Universe Research Project. Please don't tell me it's not there.
It goes straight from page 2 to page 4.
Oh, that's very clever. Right. Okay, what I will do is I will now, okay, so it appears for some reason or other that got missed off. Let me just read to you what, or can I put this up on screen? How do I do? Yes, I'll put it into the chat. Just a moment. Okay, what you need to do is get yourselves organized into groups of 3 people. And you're going to, not today, this is going to be over a couple of lessons, create a presentation that describes the principal contents of the universe. So let me just see, where is my, oh, it's over there. In there, Word, Universe booklet, there we go. Right, so let me send a message, paste. Right, so now what you have here, the Structure of the Universe project. What I want you to do is to create a presentation that describes the principal contents of the universe, including stars, galaxies, radiation, and describes the solar system in terms of the sun, planets, planetary satellites, and comets. You need to look at each of those terms. Remember, this is going to be a presentation. So I want you to put together maybe a 5 or 6 page presentation, which you will then deliver to me in the classroom. So when we come back after the Easter break, we hopefully will have some more time in the classroom, which is going to allow us to work on this project. So I'd like you please now to start. Yes, Per.
When you say 6 pages, do you mean 6 slides?
Yes, that's correct.
Okay, perfect.
I mean, it can be more, it can be 6 to 10 slides. What I'm not looking for is a 30-slide presentation. I'm looking for something concise. You can do it graphically. I don't mind how you do it. You can take pictures, you can add descriptions, you can voice over. How you wish to do that is entirely up to you. So I will put this now as an activity for you in the classroom. Date is going to be sometime after the Easter vacation. So you've got 2 or 3 weeks to work on this, but I'd like you to get yourselves together as groups now. Yes, question.
Would it be possible to have it the week after the break? Because we have the final submission of the GYR right after the break.
At the same time. Yeah, I'm not going to do it to confuse and to compound anything else. The date that I'm fixing is going to, it means you've got to be in school, for example.
Okay.
So we don't know yet what the rules are going to be regarding you coming back to school after the Easter break.
All right. Thank
But
you.
to do the presentation, I want you to do it in the classroom.
Yeah.
There, yes.
Just to recall, did you say that we can use voiceover for the presentation as well?
Well, if you'd sooner do a voiceover rather than talk during the presentation, then yes, you can.
Because I mean, if that would be allowed, then we could potentially also have like a video assignment so that you just make, yeah.
Be creative, Per. That's what I'm asking you to do in this instance. Previous years, we've had a panel of experts, and we had a newsreader who interviewed the panel. Be creative, do something different. I don't mind how you do this. It's a broad presentation. Do it how best you can.
Sounds good.
Okay.
Yeah.
I'd like you to now, please, I'll put this into the classroom. I'll do it straight away so that it's clear for you, and make sure that you have the appropriate grouping. So what I'd like you to do is, for the remainder of the lesson, organize yourselves into groups of 3. And can you send me, please, who your groups are? So I need to see who's going to be Charlie, Benjamin, whoever else, and whatever your groups may be. So can you send those to me? Get yourselves together, take 5 minutes. I'll put this in the classroom now for you. You can start to look at this and start to see any of the questions. So I will go to the classroom.